Okay, we are good to go. Thank you. Sorry, Isidora, once again.
All right, so we can start now. My name is Isidora Hennig. I'll be moderating tonight's session. So first, I would like to say a few words about the School of Materialist Research. So the School of Materialist Research is an education and research inter-university grassroots platform that offers integrated credit programs, seminars, special programs, and research initiatives that address the materialism running through contemporary science, philosophy, art, mathematics, design, architecture, and politics. SMR was founded by the Center for Philosophical Technologies at Arizona State University, the Institute of Social Sciences and Humanities, Skopje, the Department for Architecture, Theory, and Philosophy of Technics at TU Vienna, and the Critical Inquiry Lab at the Design Academy Eindhoven, and serves as a global hub for education, research, and experimentation at the intersection of the humanities, social sciences, creative fields, and the STEM sciences. So a few words about our instructor tonight. Our instructor is Erik. He is a scientist and theorist currently working in the areas of bioinformatics and evolution. His research focuses on the foundations of science, emerging knowledge paradigms, and the roles biology, culture, and technology play. He has published and presented this work globally through venues including Tunji University, Publication Studio, MIT, Curiosity Collider, Microsoft Innovation Labs, Free Dogma Press, New York University, Simon Fraser, Furtherfield, University of Victoria, Vivo Press, and Shanghai Tech. All right, so the floor is yours, Erik.
Awesome, thank you, Isidora. So I'm going to pull up my second screen, and once again, I will open up the chat, and also I have mastered the hand up system. I've mastered the system. So if you use the hand up, I get a ding. I can't miss it. Even I can't miss it. So you can go ahead and use that. And if you use the chat, also I have that up. So I should get that pretty quick. I've missed these things in the past. I sort of go back and I'm like, oh my God, he said something like half an hour ago. And but yeah, so depending on how you're comfortable, anything is fine. You can put your hand up to talk, chime in. You can just put something in the chat. You can comment, you can question, whatever you want. Last time we sort of had, the presentation for about an hour, I guess 50 minutes really, because we kind of get going a few minutes in. And then we have the potential to open it up, but I'm pretty open. So depending on what you're interested in, we had a really great conversation kind of in the last section last time. And that's totally cool with me, or I can keep going and talking. Even the parts where I'm talking to you, it will have an interactive component. Yeah, so we'll introduce some ideas and we'll get a bit of a taste of how that can work. It's a bit of an open question for me, how there's a sort of the density of the medium and what kind of works. And so I've got a couple things that I think are workable examples, especially in this slightly more general kind of framework that will give a kind of sampling of what a more extended course situation would offer. And I'm still getting used to this too. We've got this, look at this. I'm losing my body. Oh my God, okay. So this kind of works. You can see this green screen system that they have that doesn't have one, right? The Zoom has this method of kind of happening it, which is good because you got this mic and that's gone, but then, my hands. So if I use my hands, which I tend to do, I'll try to take a gander up there so that I can verify that that's actually working. Okay, so that said, some of you may have followed yesterday, maybe not. Doesn't really matter. Really, where I'm going to start is sort of taking the same framework. We're going to sort of go over the same general territory, but go a little bit deeper. So it'll be an okay intro for you to go back to the more general kind of framing of the issue. If you're starting with this one and you're going back to the other one, or if you're coming to this one from yesterday, we'll go deeper. So you'll get more of these sort of details. So it can work kind of in either way. All right. So we here on the right see deeper into the rational components, correct?
Yes.
Awesome. Thank you. So this is a repeat of yesterday. We talked about how there is this kind of inside and outside, right? You've got a kind of technological frame, you've got the laboratory, you've got these sort of objects, these apparatuses of knowledge, and then you've got the symbolic language of objects, which really boils down to logic and mathematics and so on, right? And then this will change the kind of psychological, sociological, and biological framing of those sciences. And it will, of course, also change geology, astronomy, chemistry, all the natural sciences, so-called, right? So that's kind of the framework. And then we dove in and we looked a little bit at these figures. And we talked about this European framing and these different kind of sub-paradigms within the European context, and then the context outside of that. And with that, then we'll look at a couple of different examples. So this toolkit that I was talking about that is you're able to use. We'll go into some basic but maybe interesting examples to whet our appetite just a little bit, just to give a bit of a flavor, which really is going to be all about this framing and then these tool sets that then any given learner or participant, can then use however they want to get into it. And of course, it's like yesterday in the discussions and so on, in that same way, whatever background you're coming from, you can kind of deepen that and kind of find ways to tangent out, whether it's through Poincaré, as we talked about yesterday, or through other figures. I mean, Martin just made a post about Varela, who actually was another great example. His autopoietic systems are another great example of something that was, in a certain context, and now through people like Carl has become very mainstream. And so autopoietic system is another good example of this entity that we've sort of complexified internally, and then sort of emerges to become an entity within a bigger system, right? And we'll talk more about that. But those are examples of things I'm not talking about that by all means are excellent ways to sort of tangent out and use some of the tools and then, go off in whatever direction that you're interested in. So this is the general question. We've got our different European characters, and then we can ask about other methods, right? This is implicit. So this is the first period, right? We talked about this yesterday as the early modern. Renaissance is a more common term that people recognize, tends to be early modern more recently, whatever. It's sort of from the printing press up until the Enlightenment, more or less. And so you've got a few hundred years there, 1500s, 1600s, 1700s. And then we've got a few figures that we can look at. Again, these could be many others, but we'll go a little bit into some of the different theorems and stuff that they're dealing with. And I'm calling this Euclid extended. And again, this is just a sort of mnemonic kind of, sort of contingent categories that you can use to kind of situate what's going on and frame it. So one thing that's interesting, and actually I'm going to pull up I'm going to get one of these GeoGebra things going here to talk about this. So Thales' theorem is, and we'll get to talking about Thales in just a moment. But let's get a nice illustration of this. Yeah, here we go. Okay, this is a better one than that one. This one is worse. Okay. Well, let me see if you can all suffer through me just sort of browsing, doing things that you can't see on the screen. Okay, so this is by this person here. I've made my citation. Okay, so here we have what's going on. We've got this, right? So this, we talked a little bit about our circles and our squares, right? So one question is, like, what is Descartes doing in relation to Euclid? And this happens over and over again. Like I was saying, there's not really innovation so much as a certain complexity that becomes current, it becomes constant. Bringing in functions, bringing in analysis, bringing in calculus consistently, and having a certain amount of exactitude consistently is something that becomes a current need, requirement, a certain amount of explicit scientific method. Again, we've expanded beyond this sort of network of astronomers and different sort of specialists within workshop settings a little bit more, because we've got the printing press, we've got some level of literacy, and we've got more and more people. We're set up for that conflict that Galileo can have, right? That we wouldn't have had a few hundred years before. The context was not the same, right? The tools that were available were not the same. And so the type of people that would come in and participate were not the same. And so the requirements for you to participate are different, that level of formalization. So this kind of move I'm going to talk about is there's this commonality between different cultural settings that allow us to converge on an idea of these general mathematical things, these circles, these squares, right? But this is one path that, one way we can think about it, a sort of conceptual pathway, right? If we pick up Euclid and we read through him, which is, maybe many courses in itself. Certainly a few books would fill up one very, very densely. But he is doing geometry as everybody commonly knows, right? But he's also doing like number line stuff. So he's doing number theory with number lines. He's building up, as we talked about last time, to the Platonic solids. That's book 13, right? So all of these techniques, in a sense, in the book are to construct those solids. We can look at, we were talking about this sort of Platonic Aristotelian dialogue in European medieval, Roman history. And you have this sort of back and forth. And you can also, another way to view this history is going from Plato, what do you do, right? Well, what Euclid does is he takes his sort of geometrical background, and there's this sort of history that's kind of tied to Plato. Plato really is on that human side, that sort of social application. So the Meno talks about this geometrical method as a cognitive one, right? He's really making the argument that we have these cognitive structures. We have squares and circles here. We just need, through anamnesis, and hopefully maybe if Socrates is free and around and he can give birth to these through the maieutic method, we can sort of recover these things that are already they're already innate, they're already a cognitive structure, right? So then you say, okay, well, what's going on? It's light math, but it's framed in math. He's looking back at some, let's say, quasi-mathematicians, people that are really looking almost ontologically at math, like Pythagoras, Thales. And so looking at Thales, at work like this that we're going to look at, or at least what has been attributed to him and his persona and his character and so on. And then how do you branch out? Well, what Aristotle does is he sort of finds that place between those dialogues, these sort of arguments, or Socrates kind of just like annoying everyone he can find, and then this geometrical structure. Well, what does Euclid do? Euclid says, let's fill in that geometrical structure. Or his book is a compendium of a bunch of different people, Eudoxus and others, that he has kind of turned into a textbook maybe. I think we underestimate a little bit Euclid, because I think if you look at his other works, it is clear that he's doing active mathematical and physical work. So I think the textbook argument can only go so far, perhaps. But whatever it is, now we've got documented almost a sort of detail of, in the Timaeus, we have Platonic solids, So what's a Platonic solid? Basically, if you have a polygon with all equal sides, how many 3D solids can you build? And it turns out that those are the Platonic solids, right? So you can build a lot of other 3D polyhedral shapes, but that particular symmetrical quality. So what does that mean? Okay, we've got math, we've got symmetries, we've got different numbers. What do squares and circles mean? What do prime numbers mean? Nothing, right? Although they kind of mean that, well, it's kind of an anchor, like it's something we can go back to. It's something that keeps coming up. So if we kind of learn it, then maybe we can use it, right? Nothing in the world is really quite a circle or a square, but it keeps coming up. It's always a nice 2D approximation that we really interact with well sensorially. So maybe we should learn it and formalize it a little bit, right? And that's really what the Euclidean or the geometric tradition, the sort of golden age, so-called, of Greek mathematics, sort of takes that tradition and goes deeper and says, okay, we've got these Platonic solids, let's build them. Or let's learn all these different things that are about constructing and analyzing and measuring and comparing, doing all these proofs, doing these proofs by contradiction, all these different techniques, and let's just complexify that area, right? That's one direction you can go. And another direction is Aristotle, who says, well, let's kind of boil down that geometry to its logical core and take the dialectic into rhetoric and into sophistical refutations and then, topics, and then we have this middle ground where we've got this sort of logical basis, and look at other sciences like biology and so on, right? So within Euclid, you can do, you've got Thales' theorem here. We've got this reiterated by later authors that we have the text for. And there's many, many paths to get to a Cartesian coordinate structure, and we have it in different contexts. Having said that, it's very typical. It's typical certainly of Descartes, and it's become a kind of, it's become the bread and butter. It's become a very central kind of thing that we've used throughout the European cultural tradition, right? So now when you look at, like, you get your matplotlib and you look at all the graphs, so many of these, a good portion of these are based on a kind of functional setup in an XY coordinate system, having a kind of independent and dependent system set up. And these are all characteristic. These are characteristic things we build up. So what's one way you can get from the world of Thales and Euclid into that world of Descartes? Well, Thales' theorem is one way. So we've just got a circle. And what is Euclid doing? Euclid, like we talked about Fouché and Nouat, we've got the circle and the square. And Euclid has the straight edge and the compass. The compass is for drawing circles. It's the same thing Nouat uses. And the straight edge isn't quite a square, but with the circles and so on, there's many, many ways you can get to the square world, right? And this is one of them. If you draw a diameter, if you have the exact diameter of a circle, then any single triangle you build with that has this characteristic where you've got an exact right angle here, right? So from there, you can then enter the square world, right? You can do all kinds of things with this. On the one hand, like so much math, if you first look at it, you're like, who cares? Like, whatever, like it's so abstract, like, or it's just sort of boring, or, it's in this realm of that becomes meaningful through recursion, through continual recursion, through different physical problems in the real world, and then these psychological and social ones, which I think are more, we're projecting back, and we're just going, this is the world we live in, let's make sense of it, where it's the physical questions, it's us, sorry, continually reaching into the world and trying to get a little bit more, trying to get a little bit more of a grasp. A new technology, a little bit better knowledge about how the seasons are working, how the weather is going to work, because our food depends, that our livelihood depends on it, etc. Right? So, and having said that, let me pull up this cool thing. I've already referenced it a couple times. Yeah, I'm going to do that one because it's got a nice big snake in it. Okay. So some of them have shorter snakes. So that's like, oh, I don't want that. I don't want to see that. I just want the image. Open image in new tab. Okay, so that's not very big. I maybe want a bigger one. Open image in new tab. That's also small. Okay, we need a shorter snake then. Anyway, if you're looking at the image, you can start to say, okay, well, what's going on? Who are they? Well, Fouché and Nouat, like I said, saying that. But what are they holding? What's in their hand? Well, here we're a little bit closer. So it's like food eating, you to like chopsticks or, scissors. No, this is a compass. Yeah. And then here, this is a plumb. This is a square, a sort of architectural tool or a construction tool. And you've got a plumb. So plumb is just like a weight that's hanging, and just like a level it works like. So if it's sort of hanging straight, that that you've got a perpendicular kind of line, right? And yeah, so this is what I was referencing, and this is what we're gonna look at as sort of the Iron Age, sort of one of these things that are coming about in sort of making some of the foundations in the Zhou dynasty for Chinese mathematics. And now let's go back to Okay, yeah, and so we'll come back to that. Okay, so now you get the coordinate system and you complexify it and you turn it into the thing that we know, commonly, the XY plane, the complex plane, et cetera, and more measurements you can do. You can do more. You can do more. More of this sort of geometric measuring and analysis and so on and so forth. We started to get into Pascal. Yeah. So Pascal, what is he doing? He's his wager is essentially that it's probabilistically, like if you take a gambler's perspective, if you just assume you're a gambler and you want to win at God, like you want to win God, then what do? And nobody has really done this perspective, but he's done so much, like with Fermat, he was doing so much with gambling and how you can basically by understanding the math, how you can play, and this classical probability that Laplace sort of typifies with looking at the dice and the coin that we were talking about, this physical classical, what comes to be called the classical interpretation, is something that he's dealing with, and then he uses it for theology. So he uses it for this. What is theology? I don't know. It's a psychological thing, or it's a social thing, or whatever. But basically, the idea is that, well, we're better off sort of going for theism than atheism, because the rewards, so the payoff, so it's almost a sort of, this expected utility idea that comes about. We've got Boole and Mill and sort of going from there. Now expected utility is huge in different formulations of AI, and so we should do it, right? We don't know, but like the payoff is way better. So there's a very explicit example of this kind of internalization, that he's taking something that is being developed to sort of analyze gambling that becomes probability theory, that's now hugely influential within neural nets, or unsupervised, supervised learning. The whole sort of gamut continually returns to probability and its cousins in statistics. And here he's using it in a deeply Christian cultural way, right? And he's applying those techniques that you can always take any new rational system and you can reapply it to what you might call theological science or knowledge or something like this, right? But any human knowledge system will be, adaptable to it, right? Just like our knowledge of the world will sort of become more complicated as we make these diagrams more complicated and we make these grids more complicated, then we get more into it. And the printing press is a huge factor here, just like the computer, the PC is a huge factor today in the level of complexity we're able to make common, because everyone will have this device that has this level of sophistication. Well, now at the printing press, the amount of people with a book and with literacy is sort of rising. Takes a while, by the way. This is a big, I think, open question in sort of the future evolution of science. It took hundreds of years before you had sort of full literacy. In England, you have like 1900 before you have common literacy throughout the country. In cities, though, you get this 150 years before, but still, this is hundreds of years. I think we're on an accelerating trajectory in regards to this, but this isn't something that's happening tomorrow. And the fact that the computer's here versus the fact that they are a mass tool, that you have a personal computer that's generally affordable within Western NATO, sort of society first, and then more and more outside that context. So you've got this complex sort of layering, right? And how long will that take? How long will code literacy, as it were, sort of take to come about? And you can insert ChatGPT. Is it analogous to code, and different sort of any sort of interface, any UI, which we won't get into because that's not what we're doing. Characteristica, let's do this. So this is a pretty awesome thing. Characteristica. So this is, of course, there's a couple things here from Leibniz. So the calculus we've mentioned a couple times. Calculus is very important. We talked last time, Martin brought up Bergson. Bergson sort of had this another case where Deleuze really picked up on this, I think, where he had a whole subjective world, something about calculus really got to the essence of ontology or something, the motion element in it. And it's a little bit historical at that point. You've got lots of different figures looking at calculus in this way. For Leibniz, this is also, about being and all these questions, but it is simultaneously just about how does it work? Like, how can you do these calculations? So I apologize for this. Not so great. I'll see if I can find another one. But you can start to look at it. And I mean, this is, I don't know, this is like alchemical 4-element kind of stuff straight up, right? And this is his characteristica, which is famous for being proto-binary, proto-symbolic logic, all these sorts of things. This universal language, a formal language thing, what Frege does later on, what symbolic logic's doing, what Boole is doing, what is events, we're just sort of undergirding what computation is all about now. And this is his diagram within his book, which you won't get in the modern symbolic logic textbooks. And this is straight up a kind of slightly more complex, I would say, kind of medieval diagram. Oh, they're all small. Geez, I guess this is like the size of the original scan or something. So sorry, you have to suffer through that. But basically, you've got the 4 elements here. Sorry, the 4 elements in the diamond. The diamond is the 4 elements. And then you've got these sort of qualities like heat, humidity, dryness, and so on. And he's just sort of adding these different arrows of action that they contrast or they don't. I won't get too much into it, but it's interesting because here again, we're just taking diagrams that we've received. We have this way, in the same way we sort of, we want to kind of truncate this in some way. This is a history where what was informing Leibniz to get to this point. In the case of Descartes, Euclid is totally cool. Thales is in fact he's kind of like the initial science guy, which is interesting. Coming from the Phoenicians, and in this case, you've got something that it's kind of not. Oh, it was a thing that he did, and then he also did these other things. And we talked about complex figures like Poincaré and like Newton, that if you look at their work on the whole and you sort of say, well, how are they formulating this idea? He's picking up on what exists before then. So it's almost like the printing press era and the sort of modern technological era has, in its synthesis and in its averaging, has come to look at this and say, well, this isn't something that we can sort of make sense of, And we talked about Lavoisier. Lavoisier might be a key figure in this, relating the law system, so the mechanical law-based kind of paradigm, to what Lavoisier can do in chemistry. And then suddenly we have, on the one hand, we have this magical thing, which is the Persian word for knowledge and science, which is an easy kind of cultural Kuhnian specter to work with. And then in this case, we have, well, okay, then what was happening before? And once again, we have a paradigm formation, we can say, right? So this becomes the thing, this sort of proximate danger, the closest kind of cousin and inspiration, but yet it becomes a danger in relation to finding a proper foundation for what we're doing. We need to use the law bases and these law kind of patterns that we found within mechanical contexts, and just abandon, not build on like Euclid, not sort of build on and complexify, but abandon. So this is a common back and forth pattern that you'll find throughout this history. And this is the paradigm situation we were talking about yesterday, where you've got kind of commensurability, or in this case, incommensurability. This is an example of incommensurability. And this is an internal decision of the workers. You could, come up with new branches and so on, where you'd find different ways of engaging, or you can sort of have an axiomatic foundation or some kind of theoretical foundation that will become less usable and less sort of workable, right? And this, specifically, is the sort of element system that's starting to explode at this time, right? We've got, I don't know how many elements at that point. We've got more than this, though. And so as we get up to 10 and 20 and so on, so we've got sort of this phlogiston oxygen kind of shift And then we get to this point where, okay, we need a new foundation. So we need an incommensurable shift. Doesn't mean you can't compare it, but you have this sort of complexity where the people that are working within the paradigm won't be working from that, right? And that's, I think, the important distinction, right? That's where we get to incommensurability. Interculturally, this happens a lot. Intraculturally, this is an example. Not as common, but this is an example. So that's a little bit about what's going on. You know, when he's developing the calculus, we talked about the continuum last time, and we talked about the one related problem I was thinking about between yesterday and today is the Greek problem with irrational numbers. And we have that famous story of Hippasus was, drowned because he talked about irrational things, and Pythagoras is a crazy lunatic and he can't handle that. And they're a cult, and and they're doing all these things. The Greeks, and then this fast forwards a little bit into the Greeks being unable to deal with irrational numbers and so on. Well, okay, first of all, you have in that period, in this Proto-Greek period, we're not quite at the Greek kind of golden age commitment to geometry that you have in Euclid and so on. There's a lot more arithmetical kind of things, and it's a lot more fluid and trying to figure out what are the different methods that are to be used, right? And Pythagoras is really, contributing to music theory, and he's looking at different, frequencies and their ratios, and so on. So that's one aspect. Another aspect is that what the Greeks actually thought once you get to the Golden Age is not that we can't deal with irrational numbers, but that arithmetically they're weird, right? We talked about the circle, and then we saw that diameter now. So what like once you do that and you draw that, that's cool, right? But it's once you say, okay, well, how do I get the area? Or how do I get the circumference, right? And then you need pi. And when you write pi, that's when it's like, okay, we're not going to write it that way. So it's more of a practical decision that geometry is working in the way that within the context of working with these squares and circles. Whereas if you write out that number, what the hell? Like it's just like you just can't write it. You can't write it. We use pi as a symbol. If you write it out, you'll never stop. And root 2 is the same. We had a unit square, square with one side, one here, and then you have root 2, right? Pythagoras' theorem. So what the hell? Again, if you write that 1.4, blah, 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 you're going on and on. You can't write it arithmetically. So it's more of a decision to be working with this in a geometrical way. And this is related to this problem of, well, we keep running into, we have this sort of, okay, well, there's a continuum right there. The objects are continuous, these figures are obviously, right? But as soon as we get discrete and we get logical and we want to complexify the system, we keep running into this problem where each layer of complexity keeps coming back to what I call the constant problem, that we still have today. Now, computers have brought a new level of complexity, and you've got people who don't believe, again, in the continuum because of the discrete mathematics that build the computer, So we keep running into the same sort of thing that's kind of intuitive and obvious, and yet as soon as you have a discrete system, you name a thing, you logically divide a thing from a thing. How do you get there? How do you get back to that, right? And you sort of can't. It's sort of at that, it's sort of, you could say, you could argue, I think that it's at the Gödelian foundation of what you're talking about. As soon as you create a discrete, you make a discrete decision and you build a logical system, then you've just got the foundations of that, which can't fully justify why you started with that first name. When we first name this object this or this object this, right? It's arbitrary. You're just making a decision. You're just sort of going for that, right? Now, once again, what the calculus is doing is bringing in more of these logical systems into the question of, well, let's not define just the area of a sphere. Let's define the area of any object. This is Leibniz's entry into this. In Newton's case, it's coming from, derivatives and so on. In this case, we've got an antiderivative, right? So, but the one thing to think about is just that, okay, we're defining the square, we've already got this problem. We've already got this weirdness where we want to know how we want to deal with this continuity. Okay, we'll stick with geometry and not go into this. In Leibniz's case, well, you've got this idea that if you want to do the area of any shape whatsoever, then you do what Archimedes did with the circle. We talked about this last time, where he built these polygons with tons of sides on the inside and on the outside. And then he said, well, pi is somewhere between these two. This insane number, if I'm going to write it out, well, it's between one of these two, because those I can actually measure and so on, right? And there's a similar kind of thing going on with calculus. We've got a sort of limit, right? We've got a sort of, as this approaches zero, as the distance approaches zero, we can make all these rectangles underneath whatever curve we want, and then we can get pretty damn close. And then we can get exact, right? But then what are we saying? We're saying that at that point, at that infinitesimal point, the problem of a point is another issue like this. It's no dimensions. A line has no width. Like what does that mean? Right? It kind of means nothing, but it's in a construction that we can bring in and out of the world that has real utility, right? And it has real utility for humans and their knowledge and so on. And in Leibniz's particular case, well, he has an idea of the monad that allows him to conceptually kind of work with this. And a monad is this windowless, dimensionless, ontological thing, you know, that's sort of at the base of being and of existence and so on. Yeah. And so for Leibniz to be conceiving this and conceiving the infinitesimal and the infinite and so on, he has that. And we'll see, you know, in Indian thought, for instance, they're conceptually able to work with effectively within concepts like zero, because again, they have a frame, they have a sort of cosmic idea that, you know, can take sunyata and say, okay, well, that's something that exists. You know, we know it's not apparent to the everyday Joe, but we can help him, you know. And so this is one way you can get to these abstractions, and being able to work on this abstract level is just to have a picture of the universe that has this immaterialist fundamental idea, you know. In relativizing space-time, you know, there's a lot of physicists working now that really look at what Leibniz is doing. Is another way to say, well, if something immaterialist, you know, in his case, the monad, now things like light and light speed, then you're able to have a foundation still while manipulating things that to us in an, you know, in an obviously empirical way seem foundational, right? Seems like we kind of start in our context and our space and time, while mathematically, you're starting with the symbols that you're working with, you know, and then there's different sort of ontological ways to justify that. Or physical ways or evidential ways from all what the equations are doing and how they're working in other experiments that are working on a macro level or on a, you know, within different physical contexts. So then what happens after that? Well, we talked a bit about Kant, right? And Kant is, he has what's called his synthetic a priori. So what is that? So a priori sort of means in the mind, sort of before experience, and synthetic kind of means in the world. You have synthetic, you have analytic, and you have the rough analogs a priori, a posteriori. Yeah. And he calls math, so you can imagine things that are mental and things that are in the world. Okay, there's like natural science, natural philosophy, and then there's a sort of moral philosophy and things like this, right? But then what is math? What is math? Well, for him, it's somewhere between. And in a sense, he's sort of at the end of this Euclidean period. And he kind of says, well, yes, it is in the world, right? It's synthetic. But because we have these mental structures that can make sense of it, right? And so he's saving Euclid, but in a way, he's subjectivizing it to a point now where that non-Euclidean world that we got into is sort of ready to be explored, or at least it's one factor, you know, that's contributing to that. So that's one thing. We've talked about Lavoisier in a couple of contexts, and it's really, I think, his use of physical law and bring it to chemistry. You know, you definitely have law-based work in chemistry. Pascal is one example that already exists, and Lavoisier is a contributor to that. And Laplace has a sort of interesting addendum. We talked about him in other ways last time, but he's also, his way of dealing with probability is interesting, because that demon that he has that sort of popularly is known as, oh, it's like, oh, we thought we live in a determinist universe, and now we know it's all kind of indeterminate and you never know and so on. This is a bit like the Bergson-Einstein debate. There is no real comparison between the subjective idea of what's going on and the fact that the math is leading you to actually a more complex math, right? Which is really what the math is doing. What's happening in the 20th century is that we're getting, not just are we doing frequentist probability, but we're getting into those and we're making each of those entities probabilistic. So it's increasing the mathematical abstraction, right? And this is really what the demon is all about, right? It really is that famous quote that I don't need, you know, where's God? Napoleon says to Laplace, and he says, I don't need that hypothesis, right? What's going on there? Well, he doesn't, right? Because through every single question, state questions and physical questions, he can reckon with just through the sort of probabilistic framework, right? And at this point, we have Christian law is out, right? We've got the nation state, we've got the American and French revolutions, and this is big in terms of the sort of crisis that comes out of this, right? We have this romantic kind of rebellion against this, and we've got this sort of how do we do secular law? How does that work, right? And historically, when we see analogs of this, this is really an expansionist question. It's a militant question. It's a question of scaling. When there's enough flux within a society, they have to go to a sort of pragmatic frame, and you can do it, right? But this deculturalized kind of model will create the romantic rebellions, right? Create these romantic skeptical kind of counter rebellions, and we'll also have a kind of pragmatist bent, right? An engineering focused bent. We talked about the scientist careerist kind of turn and all of the practical sort of technological elements to the American mode and the modern mode of science. And we can actually say science now, right? We're no longer saying natural philosophy, we're really saying science because that's the terminology that's now being used for the first time. Mary Somerville was the first to use the word. And then you have people like William Whewell, who by mid-century is using the word. And by the time we get to our friends here, like Peirce and Poincaré, they're using science too, right? Poincaré says science and hypothesis. Peirce talks about science, and those wouldn't be the words for what we're retrogressively trying to use. So this is natural philosophy, but with this pragmatist bent. Yeah. We talked about a lot of this enough last time. I'll just say that, Peirce's one way to frame, Martin brought up fallibilism and falsifiability and the connection there. And that's absolutely one that I think we went over. But what's interesting is that Peirce has these sort of Venn diagrams that, again, we sort of say, okay, it's no longer geometrical, but it always is, right? So, I mean, and let me explain how I mean that it's the axiomatic system of Euclid that we're questioning the parallel postulate. We can't prove it. We're then saying, well, maybe we just won't use it. And then we're rebuilding geometries, right? Riemannian geometry is a geometry, right? And it's something you can put on a paper. And this aspect that we have these sort of, very abstract kind of logical arithmetic kind of components. And then we've got these kind of pictographic, metrological, components. These are the two symbolic aspects of how we're continually working on computers. It's the same thing. You've got the code, you've got this sort of output, right? You've got the graph and you've got the equation. And Peirce has a really, this is an interesting thing. We don't talk a lot about him in terms of how his full logical system is relating to things like Venn diagrams. Well, he does his own Venn diagrams and he adds elements to it, and they sort of account for more. We haven't talked about Carroll much. Carroll also has his own way of doing these diagrams. But then you say, okay, well, within these new worlds of different kind of set systems of logical atoms or of sets or of, these new kind of axiomatic entities, we've got a bunch of systems that come out, right? And we've talked about a bunch of these, and I'll just talk a little bit about Peirce's full continuum because he's got kind of this semiotic kind of idea, right? Which is on one level. And Peirce is he's like this infinite tree of different trinary kind of things coming in and out. But one is that you've got kind of semiotics and you've got logic and then you've got pragmatism, and we can sort of reframe that here, that you've got the semiotic system is sort of any sign at any time. And then you've got a logical system, which is sort of analogous to his complexified Venn diagrams, or, what you can compare to the Venn diagram. What's contained in what, and you've got overlaps, and then all the logical and nots and so on. You can construct with those. And they're the most common thing. When you look at and not, and you look them up, you get these geometries, just these straight up kind of overlapping spheres and so on. But there's a fallibilist element. So he's reckoning with the new science, this new laboratory, which really we can call a laboratory now, not the gentleman scientist's attic. No, this is a place of labor. This is a workplace where people have a job and they have a career, and then they're doing natural science out of that, right? So that pragmatic element, or making a thing or something, tends to be more of a focus than you might have gotten in the privileged gentleman philosopher's attic, right? The concrete and the abstract and that kind of back and forth. So yeah, what is the logic for? Well, it's ultimately for undermining within the lab, right? Falsifying or making fallible, and and then abducting from, sort of it being incomplete, it getting it wrong, but creating a frame that you can then go, okay, that failed, and that failed, and that failed, and that failed. So now this is sort of the creative component, and I'm going to go a little bit deeper in the history in order to construct this in different ways. But briefly, we talked through Gleck and how via, for instance, Poincaré, and actually historically, Poincaré is the place to start. Like we said, he's so entrenched in so many different mathematical fields that he's part of that conversation. The only critique he really gets is that, well, he didn't do it as formally as we want, and he liked to move on to topics, when he felt like he had sort of addressed them satisfactorily. But chaos theory is definitely one of these. Now, what is Strogatz's work? We talked around it, but one key book here is Sync. And Sync is basically like fireflies. So you have fireflies, and fireflies in a group will start all blinking together, right? And you can model this and create models, and they're all separate and so on. Flocks are kind of similar. What's going on here? Well, it could just be a local sensorial thing where each firefly is kind of looking around them and trying to fit in, seeing the dance that everyone else is doing and being like, I don't want to look like an idiot. And then once they're all blinking together, you leave them for a while and they're all blinking differently, and then they start all blinking together. And he is an example of like the Millennium Bridge in London was like kind of faulty because it had once it started swaying, everyone was swaying together on it, Anyway, they had to fix it. But this was the thing that was just happening. And was it voluntary or was it not? Ooh, it's mysterious. But this was the thing that people, would sort of react around them. No one on that bridge had like a meta view, right? And yet each of them were sort of looking at it. And I think within my formulation of getting deeper into these structures, a question you can begin to answer, just as with chaos, you reach a threshold, and then now you can sort of contain all that pre-chaotic stuff and all that post-chaotic stuff, or something like that, right? You can go from a liquid to a solid to a gas to a liquid to a solid, and then that phase transition allows you to say, well, solid is a word I can use that actually has a meaning, and things I describe about the solid won't necessarily apply. So that emergence or that shift, that transition, phase transition, is useful to demarcate, right, between these different sets, and then get into your logic within that system. And what we can ask about the fireflies is, should we consider them as one unit? Should we just talk about these firefly clusters? With birds, should we talk about flocks of birds? Should that be one entity? And then we can describe what's going on in that entity. Somewhere between these two are the networks that Barabasi did. And we talked, I think, enough about this. But again, you've got this sort of entire network, or you've got these different hubs that start coming out, right? They start differentiating. Different concepts related to this are the sort of prior, arrow that Martin had brought up, and how you sort of start developing new orders, right? So you go from, let's say, a network that is just equally or randomly connected, right, to something like the internet, or cellular networks within your body, different like protein metabolic pathways that tend to cluster around these hubs. So ATP is super important, and this is super important. Okay, so now if we're describing it, shouldn't we just kind of learn about those hubs? If we want to talk about social media, we'll just pick a few instead of learning about the 100 that are out there that have like 2 users. And so we start deciding what is the key component, what is sort of that causal essential component to describe either the whole system or that entity itself or what have you. Yeah. In Wolfram, we specifically have this. Again, these are all authors that are using new science. There were psychological authors too, but there's not much to say about them formally. Paul Bloom, Brodie, memes and desire, pleasure, sorry, in Brodie's case. But, this is, I think, the formal systems they're using are really coming from here. So there's a lot more to say about it here. Wolfram, cellular automata, the game of life is sort of a classic example. I'm sure you have a square and you give it rules, and now we can you can start to see how how we can compare this with other systems where each flock each bird in the flock has internal rules, and then something emerges out of that, right? So then that might be the entity you want to focus on and what's going on. And Game of Life, for instance, has like Gosper gliders and all these different formations that out of these rules come out, right? Yeah, and then there's many different cellular automata that Wolfram himself, he kind of comes after, but then creates this formal basis for what's going on. And so, yeah, so then then the question is, okay, well, let's look at more of these different examples and so on. What's coming next? Well, what came outside of this context? All right, so we've got, again, these categories. They're different received categories and other ones, and we're going to give a flavor of what's going on. Historians tend to call this rhetorical. I don't think it's accurate. This tends to mean that it's all sort of written. It's not. There's symbols, and we have this idea that it's rhetorical, and then let's see, syncopated, and then symbolic, I think is the last one. But it's not really accurate. You kind of got a bit about everything, a bit all over. So the idea is that we just write it in words, and so we write it in poems, which we're still doing in the Renaissance, you know. Verses, we have some symbols, and then we have more or less full symbology. So it's not quite accurate, but perhaps there is a kind of tendency. We have more and more formal vocabularies that we're unifying. That's I'll concede that. It's not really describing the geometrical complexification that I've been focusing on, which I think is the other side to this. Okay, so what are the kinds of things that I've been talking a lot about, these different recurrent things, these different things we keep coming up with. And just to note, I'm just focusing on documents that we have and how we can reproduce these, because these you can actually learn how to do the problems, right? And there's all kinds of stuff going on before this, right? There's just inherent numerosity. Humans have numerosity. We have hands, we count with, all kinds of things going on. Other animals have numerosity. And there's all kinds of documents and structures. You know, we're talking about the Giza pyramids, and you can look at things like Stonehenge. There's math there. There's all kinds of measurements and so on that you can verify by seeing how it's situated at an equinox or something like this. And yeah, but I'm not covering that because it doesn't explicitly go into how you can actually redo that equation and then compare these different mathematical systems. But it doesn't mean that we don't have this. There's obviously so much that leads up to this, and so much that we're already doing in very similar ways in different contexts that we're now making more explicit, right? And there's a level of formalization and stuff that is what's been a constant theme here, right? We keep adding more and more complex formality. So what are the things that get covered? Well, you've got things like areas, you can see, right? And here pi equals 3 is good enough, you know. You've got eclipses being predicted, so the astronomical tables that are being produced and the estimation of the sky is good enough to give you a sense of an eclipse. We talked about shadow length and different in light of the structures I just mentioned, and how that gives you seasonal information in addition to what time of the day it is, right? The triples we started to touch upon with root 2, which is right here. But in this case, you have a table of not just the 1 root 2 square, but a whole pile of them, right? So we have like the 3, 4, 5 square and so on, right? Or triangle, sorry, the 3, 4, 5 right triangle, half square. And then they're doing areas of weird things, trapezoids. Cool. All right. So, and then there's another just sort of, that gives you sort of a rough idea. There tends to be a little bit more transactional. Babylon is Mesopotamia is sort of these small kingdoms that are trade heavy versus Egypt that tends to consolidate a little bit more. And a tendency a kind of tendency with that is that you have more focus on calendars, on knowing navigation, on knowing what the sky is doing versus having more knowledge of sort of taxation, cadastral information, geological information. So one shorthand for that is calendrical versus geological organization or control or what have you. So here we have 3.16, not bad, right? Good to 1 decimal place. A frustrum. So you've got, this makes sense just in light of the pyramid, right? That a frustrum, is basically like, just imagine a pyramid and you cut the head off, right? So then can you get the volume of that? So in here, in the Berlin papyrus, we've got quadratic equation and a solution. And I want you to think about, when you think of quadratic equation, think of squares. Okay, think of squares where you don't know the variables. This is really what's going on. When you have x squared plus x blah x plus some number, you're really trying to figure out what a square, what the area of a square is, or something to do with that square, because that's the x squared. And then maybe you just know some other things. You just know a length, or you just know something else, right? And then can you get the full information about that square? And this is what it's all about. And you've got all these sort of, these are, again, school books, or they exercises. There's different things coming from different contexts that are trying to train people to get used to working with these symbolic notations, so that, as an engineer, as a builder, as a worker, whatever, they can go out in the field, and then they can sort of use these and internalize them, get them as rules of thumb, and be able to, gain a consensus of what's going on and what the measurements are of what's happening and so on. Surveying, surveying. This is on a geological level, on a civilizational organizational level. This is key. And yeah, so this is self-explanatory, but yeah, this is also a very simple classical thing for why are you doing it? Why are you doing it? Well, to tax, right? To tax, and also to be accountable to that in a way that's traceable, and to see how good the crops are doing, and to see if we want to make changes and so on. So these are really about these kind of earthly kind of tendencies. But again, I really want to emphasize that we've got all this continuity. We really do have a kind of progression, because people keep repeating the same things. There's all kinds of geological stuff here. There's all kinds of astronomical stuff here. There's no question that you're always doing both. It's the full gamut of what's in the world. And then again, that eventually will start reflecting on what sort of stories and stuff you're telling, or what kind of psychological, sociological idea you have. Again, I've got a kind of, okay, so syncopation means there's a little bit more symbolic kind of use. I've added this because I think within these contexts, you've got almost pre-civilizational situations, or exilic ones that, that are even more mobile than you get in a sort of warring states situation. But let's look at these. It's interesting how sort of, it's interesting to see how there's a convergence, and then there's a very original kind of oh, and by the way, I'm going to go another 10 or so, and then we'll have a discussion. Yeah, it's interesting how the differences in how we construct and we get to, we won't get to it. I'll just go into one example, but how, the Babylonians are working with base 60 and base 12, to some extent. And we still have this in our calendars, and in our clocks, and, in different places. The measurement of a circle is 360 degrees in the degree system. And that takes a bit to get used to when you do how they set up their equations. Egyptians have decimal, more or less base 10 system, and so do the Chinese. And we have this in these tortoise shells that they have, and they had a decimal place value number system. So that means that they had negatives, and they had they say a place value concept of 0. This is, we can discuss what, what's the difference between that and, maybe it's not a thing in itself, or, I don't know. It's a little bit vague, but we tend to give it more to the Indians, not this Iron Age sort of Indians, but what follows. And yeah, but effectively speaking, this is a really powerful this is really the pioneering decimal place value number system. What did the Egyptians has? Well, again, you had kind of it's kind of place value, but anyway, this is something that we'll take a look at in a second. The I Ching, you may have heard about. Basically what you've got is a binary set that can get up to 64 permutations. It's also represented commonly as an 8 times 8 table, again 64, right? So the hexagrammatic system, you've got long and short, 2 options, and then when you have 6 of them, you go 2 to the power 6 gives you all the permutations. Counting rods, which we'll look at how this system actually works, is in the Tao Te Ching. And this is sort of the original hippie math statement, It's like, if you're good, which we won't be, we'll be bad because we'll use them. You don't need them, you just need to feel math. You just need to like feel it in your soul. And then of course you've got other things. You've got the Shipan, which is the Luopan is a more common name later on, but these are astrolabes. So you've got these different things that are measuring. Again, in the Nuwa Fuxi diagram, Nuwa is the sky. Mythologically, we tend to give, it tends to be, this is never universal, right? Sun is a man, moon is a woman. Not always in Polish mythology, no. In this case, sky is not a man. There's no earth mother. No, it's an earth father and then a sky mother. And it's the circle that is corresponding to the sky and the square to the land. Not universal, but it tends to be that, yeah, the circle, and the astrolabe is a good example where you actually have, to get better, you'll start using things like conic sections, but yeah, circle becomes relevant. And so, you know, the horizon is a circular sphere, right? Is a half dome, or it's a circle. And these astrolabes give you enough information with a circular end, you know, to be able to get constellation information, then know where you're situated, knowing the season and so on, right? Which you can also, so you've got basically the pole star and the North Star, and then with the seasons it rotates, right? The precessions make this shift, but that's over a long period, so we won't think about that. But you've got this shifting, and the astrolabe basically is able to, you know, use that as a map, use that as a clock, use that as a navigational system and a sort of time system. Now, how do the Indians develop these things? So, you know, like what's going on here in the Luoshu square is a magic square of 15, which magic squares just mean that all the different horizontals add up to 15, diagonal, you know, vertical. What's going on here? What this collection of things, there's some sort of ritual culture or something that's going on here. It's hard to say. In the Indian case, there's very explicitly, it's not just that, it's the geometry of ritual. So it's setting up these different altars and so on. Yeah. And we're back to root 2 because we're trying to make squares. We're trying to make these square shapes within our ritual setups. We're back to quadratic equations. What did I say? Think of quadratic equations, think of squares, right? Quadrature of something, the squaring, making it into a square. Famous example, quadrature of the circle, trying to square the circle. Why would we bring the square and the circle together? Who cares? Like, just, well, the square is easier to work with in some ways, right? We can get these sort of measurements. This is the same kind of logic that Archimedes is getting to when he's trying to create these big polygons, because we can actually, you know, definitively kind of measure that, turn that into like a normal number, and then we can start to approximate this this strange curve that with a rope or a string, well, it's not really a problem, right? But then once we get into discrete issues, we're back to that, what is essentially different permutations of the question of continuity. The Satapatha Brahmana talks about the motions of the sun and moon. Again, astronomical knowledge from this. And one thing that's a little bit unique, a little bit pioneering, that fits with the fact that the infinite and the infinitesimal, the zero and the bigger than anything you can imagine, really the Indian mathematicians and thinkers and scientists are pioneering in. It's because they really have a cosmology that reckons with large things very early on. So you see they've got numbers up to 10 to the power of 12. And then here they've got Ananta, which is, you know, a name for a number that's, yeah, I mean, this is a trillion. If I'm not, no, it's 10 trillion. And then, yeah, there's 100 trillion. So anyway, so this is at that time is as big as we're getting. Why get that big and so on? Well, you know, in the case of Leibniz, he's got this ontology that can make sense of these sort of things, these infinite things. And so you've got a vision of the world that fits into this, and this coincides with the devices you're using to build your cosmology. And we've got this nice statement in the Yajurveda, one of the key Vedic texts, which is the key Veda's knowledge. And these are sort of the first Indo-European texts we have within the Indo tradition. If you remove a part or add a part, this is anti-Cantorian, right? Or at least his power set version, you know, his kind of cardinal idea of sets. When you have subsets, you can make them bigger Anyway, we don't need to get into that, but here it's just infinity, man. Like, yeah. So, and I'll just mention briefly here, Phoenician and Hebrew systems. You can read the Bible and get these cubits and palms. A palm is this, right, which is 4 digits, just finger widths. 4 palms are a foot, and a cubit is an elbow to the end, which is 1.5 feet. What's the base of these? Well, it's base 3, base 12. What's the best number system? Well, you know, there's a lot of base 12, and decimal works in a lot of different ways. But in a lot of ways, 12 is better because there's more divisors. It's more manipulable, and so it's, you know, when you have half a dozen or a quarter of a dozen, you know, there's different ways of working at it, and that's, you know, English kind of common measurement being inherited from these different 12 duodecimal systems. And then the numerical history, if you add up all the kings, you look at the symmetries here. Normally we would go for decimal symmetries. We would just say, oh, it's like, you know, it was 100 years ago or 200 years ago. No, they'll go multiples of 12. So you have all these multiples of 12s that are somehow round numbers for how they're doing, not really histories, right, but sort of symmetrical pseudo histories that kind of get at it, but also just kind of look nice, numerological in some sense, right? Okay, so 2 key figures in the beginning of Greek math, Thales and Pythagoras. Both of them have Phoenician heritage, and I think 1 parent, something like this. Anyway, so you've got this kind of combination between this kind of these nomadic Phoenicians, their cousins, you know, eventually in exile, but coming from the same stock, Western Semitic cultures, and you've got 2 kind of things going on here. I don't remember exactly what it was with the ship. I think it was a distance, but it was something practical in navigation that Thales is attributed to him. And then you've also got his sort of like water is the foundation of all things and so on. So you've got a kind of metaphysics, and then you've got a kind of practicality. To me, it's a sort of transition to the axiomatic and deductive basis of the Greeks averaging everything, and then what the Phoenicians were doing before that, which was maybe a little more pragmatic, at least what we still got. There's always the question of what's remained based on what culture we've inherited, and that Kuhnian specter we talked about. Pythagoras again, music intervals, and then you've got, you know, drowning of the irrational. You know, you've got this sort of this ontology of pure number. So it's interesting though, because you've always got these that you've got a kind of cultural system that's built off the abstractions of these different numerical systems. This is kind of the unique thing. This more or less sets us up. Right, and I'll skip over all this so we can get a couple of examples, and we get into the different genealogies and developments of these different cultural systems. The Chinese and the Indian are really important, especially when you get through the so-called Dark Ages in the Western context, where still things are going on, but not quite as much. And a lot of the advances in the how exact our measurement of pi is, you know, how exact our measurement of root 2 is coming about. And we'll look at one thing now. So, well, what's going on in India within this period? And now we've got it within, so we've evolved from the sort of ritual context to a kind of cultural context. So we've got these sort of grammarian figures. We've got this incredible freaking number. And here I'm just going to show you what's going on with Pingala. So Pingala is looking at meter. Yeah. So this is a long syllable, this is a short one. Yeah. So this is 2 beats, this is 1 beat. So if I create a pointless poetic meter of monometer, what are my options? Well, I can just have a short one, and that's 1, right? So if I go dimeter, and what can I do? Well, I can do 2 of these short ones, right? Or I can do 1 long one, right? So I can go ba or but. Trimeter, what can I do? Well, I can go here, and I can have 2 1 1 2 or 3 of these, right? And I think I'm not going to write this out, but I will. This is something you can go through, yeah. And what you get for 4, well, let's see. Okay, let's see if we can do this. Oh, what? All right, so here for this one, we can go here, right? We can do that, or we can do this. So then how many more do we get? Well, we get, you can imagine, sorry, I need to add that. Yeah. And then we can move this through 1, 2 times. So then we got 4, and then we can do all red, right? And then how many do we get? Well, we get 5, right? And then it turns out when we do the pentameter, we do all the permutations, then we get 8, yeah? And then we can go on and on and on. What is the sequence? Feel free to chime in that we're starting to map out here on the right. What is the sequence? 1, 2, 3, 5, 8. After 8, it's 13. Feel free to use the chat. Put your hand up. So this is the Fibonacci sequence. Fibonacci used rabbits, and he used rabbit, rabbit copulation and how they then expand. And here we've got the use of poetic meter and the permutational limits within a binary syllable set and how many you can come up with. 2 totally different things converging on a system we haven't talked about, the Fibonacci sequence. But of course, the Fibonacci sequence, very, very recurrent now as well within different mathematical systems. And we'll just look at what these counting rods are. So let's talk about this decimal system and how this works, what's going on. So these are the things that a Taoist does not need to count, but a non-Taoist can use them. So this basically is 0 to 9. This is 10 to 90, and this is, the hundreds. So this is the zeros, or the ones, the tens, and the hundreds. So how these work is basically you just keep doing. You have 2 different systems roughly. You just keep adding this, and then you do this, and you want to get rid of this. Once you get to 5, then you go, oh, okay, what do I do? And what you do is you bring in one of these. So you bring in this for 6, and then you get rid of all these, and that's 6 right there. This T shape. Right. What you do in this case is you do the opposite. You stack these, and when you get to 6, then you put a vertical one. So 6 in this column will look like this. Yeah. So now we'll just look at, well, what are the different numbers that are just written here? Well, this is 1, 1, 1, right? So this is 111 written in the rod system. And this is 66. Yeah. So you've got place value, you've got, and so you can go on and on with this system. And I think with that, sorry, this time I've gone a bit over. Yeah, we'll, it was always open to questions, but now it's like extra open, I can also go on. I could kind of wrap it up with different ideas, but yeah, this is basically just a bit of a taste of how we can converge in these different systems and these different geometries that aren't really, it's not like we come up with a different math with other cultures. This is kind of this lost civilizational kind of conspiracy thing where we just kind of have this whole alternate thing, or we're way more sophisticated. No, we're doing the same thing. We do have a level of sophistication we develop in the scientific revolution, but we've got all kinds of it already. And the interesting thing is that in innovation and contribution, which is really in an open scientific context, something that's of interest to me, we can learn so much about, how to arrive at that. When you think of a square, how many ways can you think about it, right? That's kind of nuts. But yeah, it's like the ways in which you can arrive at root 2 and pi and a Fibonacci sequence or any kind of mathematical thing, entity, symbolic sort of pattern, there's a whole bunch. And when you go to these other systems, you kind of see these innovations that haven't been picked up on, right? These different paths to arrive there and to get an intuitive relationship with what's going on, different geometries, different pathways. And in the open science context, when we go back to our different, contemporary workers who are saying, okay, here's a new science. Okay, well, what is it? What's going on? All this hype about AI. I mean, this could be a whole tangent here. Well, let's look at some basic stuff. Let's look at what's actually going on. And the toolkit that we've laid out so far, preliminary as it may be, gives us, a lot of the language that we can just sort of look and demystify, our new cultural context for this, which is this, this like TED Talk transcendence. I don't know, it's this like ridiculous kind of thing where you're never talking about what's being talked about, probability and the, this political thing that already, Laplace is sort of organizing people in this mathematical way. And this is one idea in secular organization and secular kind of secular population control or organization or ordering that becomes something that is recurring in different ways, right? But yeah, if you look at this from the perspective of a creative, a writer, an academic, a scientist, someone who's trying to formalize, invent symbolic systems, invent logical systems. We didn't talk about it, but the diagrammatic inventive is not just of the Peircean, the Peirce I was talking about, but all the different diagrammatic possibilities that you can have. That really is what these different geometries are talking about. Well, what is the space where you can be contributing to that or inventing within that world, looking at the grammar of science and of math and formal systems and work from that. And my contention is essentially that, well, by getting to the core of what's actually going on and looking at how that's framed and where that comes from and all the different potential paths outside of that, whether they're future paths or they're past paths that have been left behind, then we've got this sort of this toolbox that is possible tools for working with and innovating and contributing to different scientific and academic categories. So I right now we've got a bit. I know that Katerina had a couple of questions, so she already blew it. She already let the cat out of the bag. She's got a couple of questions, and we've got just that kind of time remaining for that. I am still open to chatting, but I'm even more open to people raising their hand. And it came up on my screen. It's so awesome. I ticked the box, and now it works so well. And we've got a question from Bryn. First of all, welcome. And oh wait, how do I do this? Yeah, I think you can.
Hi,
just talk.
Hi, Erik.
Hey.
Great talk. Thank you. Been a long time.
Thank you so much. Yeah. Thank you for coming.
No problem. I had a question about like the kind of arbitrariness that you were talking about involved in sort of like foundational logic systems, and yet this sort of like non-arbitrariness of these like real numbers such as pi and like square root 2 that keep coming up in geometry, and like how those two things of this arbitrary relation of like how those systems end up being set up, and this sort of like non-arbitrary, I guess you might call them like invariances or constants or regularities, and how those kind of two things interact. And I'm thinking specifically around sort of like construction of models, like like and like different models like efficacy or use value for like specific tasks and that sort of thing. But like just in terms of like how those like construction and sort of invariance sort of interact in some of these systems.
Yeah, that's a great question. Yeah, thank you, Martin. I did that, but I think Bryn, you need to coax her to turn her camera on, because I think that's what you meant, is you couldn't see her. But that's not my fault. That's not my fault. That's her autonomous choice. But I did turn it off so that if you do have your camera, you'll get the full screen and all the glory. And if you want no glory, that's okay too. Just incredibly incisive questions with relative anonymity. No, that's a really good question. So I mean, and I like the way you use non-arbitrary, because that's it, right? This is a sort of, this is the Platonic gambit. And the more that I'm doing this, the more I'm like, well, within this technological space, yeah, I mean, this is what we're talking about. This is like the best we can know, and this is the most we can know. And in the sense that you set it up so well is in the sense of recurrentness and of invariance and of non-arbitrariness. Well, okay, we've got all these formal systems. Yes, they're arbitrary and they're very human. Is mathematics the language of the universe? Well, this is a very human system. We've built it up. We've got these different things we describe on. Our hands and eyes lead to us, working in these frames that we can manipulate and we can visualize within that frame. Superhuman stuff, right? And yet, what are we learning about, right? We can imagine all these organisms with all their different systems, but what do they converge on, right? Even forgetting that they might be using mathematics or not, right? That in some way they're getting some formal knowledge, some predictive participatory knowledge, every organism on the planet in different ways, finding their niche, surviving in their different ways, right? What's going on? What is that real, right? What is, let's say, a convergent zone of 20 different species? What is it really, right? And what is the invariance is, yeah, it's pi, It's exactly what you're putting down in your question. There's no question, I think, that when you look at the different cultural systems, they're arriving at these things in very, very, very different ways. But the Fibonacci sequence keeps coming up. I hate to be a mathematical spiritualist, but fractals they're coming up, man. Like they're something that once you start identifying them, you formalize them and you label them, then you're seeing them, And pi and root 2 are even more, they're like the deeper hippie mathematics. They're like, how many ways, like you look at something like Pythagoras' theorem, this is like a trip you can go on and look at, like, I don't know, proofs of Pythagoras' theorem or something like this. There's just so many. There's way too many, And these are like permutations, and almost like what a proof does is kind of make it obvious. Like it explores it fully to a satisfaction of anyone who's assumed those different axioms. So despite all that arbitrarity, today it's like we keep converging more and more on these invariances. Okay, so then I've kind of talked around what's that final thing that's at the core of your question. Well, I don't know, but I think there's a Platonism that becomes more and more apparent, a kind of Platonism, a Platonism within a technological context. That is to say that within whatever our organism is doing, as we keep coming up with these things, what is the circle? And we're using the circle for astronomy. Well, it's not quite that thing, and yet we keep converging on it, and pi is a part of that. And whatever that, sorry, the pun, but circling around pi has something to do with the universe, or it's the best picture we can get of the universe. There's, for instance, these dung beetles where they did a test, they covered their eyes, they put them in a planetarium, they couldn't navigate. The conclusion of the experiments is that they use the sky, right? So we're not the only organism to use the sky to navigate, to orient, to know where we are, to know when we are. And so this is a tool, this is a kind of common tool, right? And it's, it's real, it's in the world. Well, we tend to use these written symbolic systems because that's what our sensorium is set up for. But what are they describing? Well, yeah, I think that once you get past all those arbitrary systems, we have some kind of realism, right? We have some kind of realism I think we can't get away from, and some kind of commitment to those invariances, that was kind of what Plato was on about, right? Although, this version is highly complexified by a plural formalism and, and a lot of the constructivism and so on that Martin was bringing up yesterday. But yeah, I don't know if that gets at what you're. Oh, thanks. Yeah, cool. Great question. Is Katerina still here? Oh no, Katerina isn't here. Oh no, she is. You still have those questions. It's okay not to ask also.
Yes, I am. Okay, it's just one very simple question. I'm not sure if I understood well whether you equate rational thinking, rational thought, rationalism, and mathematical thinking, whether these two forms of thought are the same thing to you. or are there other formalisms of thought that are not, essentially mathematical? Maybe they operate with some element or some degree of maths, but they also have they're simply of a different nature as far as their the formalism of thinking, the abstraction of procedure is concerned. So, or does it all come down to mathematics in the end?
Yeah, I don't think it does. I don't think it does. But to elaborate that, I wonder, do you have a specific thing in mind that we could maybe use? Is there a specific reference, a philosopher, thinker, or something that uses a type of rationalism that you think does not?
Well, take Darwin, for example.
Okay, good. Yeah.
Take in my area, social sciences and humanities, I don't know, anthropology, ethnography. This is so, well, there is a procedure of, there is a formal procedure of processing data. So it is not as exact as mathematics, but on the other hand, mathematics can be very exact and abstract, but sometimes useless, right?
But not applicable, right?
What is rationalism in the end?
So, no, good.
As mathematics,
So, and I'll jump off that Darwin. That's a really nice example. And I definitely think no. And I definitely think that this is sort of really taking, first, it's not saying what's the scientific method. It's more how is it used, and then what are the ways in which that's explained, right? And it's not saying this is rationalism. It's saying, okay, how is rationalism used in relation to scientific method, right? It's not just mathematics, as we looked at, for instance, in Peirce and so on. You've got and Boole. They're really thinking about logical systems, in a way that, well, I think, we can fruitfully bring in Darwin, and we can bring in sociology and anthropology. Does Darwin use equations? No, he doesn't, right? Is he working rationally? Absolutely, in some sense. Can you build equations on that? Yeah, right? So, I was reading Gödel.
Linguistics also, Erik. Linguistics originally, I mean, as in Saussure and what followed, and the studies of natural sciences, comparative grammar, so all of that.
So let's look at Pingala. Pingala is actually another good thing to look at in relation to this. He is someone working in language. He's working in metrology and and sort of poetics and so on. You don't need. It doesn't even necessarily have really any mathematical thing, right? So there's a number of ways to look at this, right? That we can, first of all, we can rethink about so many things that we've covered already. We can talk about rhetorically. This is exactly what's meant by the rhetorical and part of the syncopated sort of histories of mathematics, right? So, but again, to return, my short answer is that, no, this is like the elements of rationalism that we can bring over to scientific method, right? You've got ratios, you've got these different comparisons, but you can do that verbally, no question, right? But these are ones that we can bring over, and there I think mathematics is just it's a solid framework, to explore that and to go deeper, to then be able to look at what is actually meant by methodologies in science, and also have some avenue into some element of of rationality. But so much of this is so the Gödel example was that he wants to look at this statement is false, and Gödel numbering is in a sense about taking that and saying, well, let's make that into this theorem is incomplete sort of thing. Can we numerify it? Can we turn that into equation? So much of the historical text that we have, even going back to the Renaissance, they're writing these in poems. They're writing these rhetorically. Indian mathematics written out, like, in fact, kind of a large majority. And what's going on in those texts? Well, you could just approach that without ever mentioning math and say, well, they're just reasoning. They're just reasoning, and they're going through this reasoning in different ways. All of the sciences you mentioned, to do with language and sociology and anthropology and biology, they are part of this internal map that I was talking about. I don't think there's any reason they can't be as precise as what's going on externally. I think there's just less, there's more of a moral cultural conundrum there. There's a kind of cultural bias enveloped in that again, a bit of the specter from Kuhn, we're just more, it becomes more contentious as we relate that back, right? So Varela, that we were talking about before, and Carl Friston, he's using that to talk about consciousness, the structure of consciousness. This is going to be contentious, right? Varela has this contentiousness because as soon as we mirror it back, suddenly it's like you've got people who don't have those same frameworks, you know? And I think when we're talking externally, we're talking naturally, there's just less contention. And we tend to build that there because mathematics and this what you might call more complex rationalities, or, you know, symbolic ones, tend to be mapped around this, right? It's a useful language for building machines and for mapping the land and the sky, but it's not so great for talking about these human things. And yet we could, and we keep adapting them and changing them, you know? So I think, you know, all the disciplines you're saying can be hyper mathematical and hyper rational. And there's examples of that, you know, what I'm doing here as, you know, there's a lot in human evolution, there's a lot of crossover with anthropological questions, but they're just going with the data, right? They're doing the mathematical, sociology, biology, psychology, all that stuff, right? And then people react. In that discipline, people react, right? In art, if you go hard with the math, philosophy, you know, this guy Kevin Zollman I'm reading, he brings game theory in there. He's bringing simulation models. Not so cool. Not so cool. It's more contentious. Doesn't mean you can't do it, right? But like you were saying, you know, at some point you're like, okay, well, you're bringing all these models. What does this have to do with anything? I can reason in other ways. I can reason in more human ways. Why don't we bring this back to rhetoric,
It's
debate, and so on? You know,
it's not that. It's not that. It's not taking sides and being against mathematics because it's inhuman or whatever. It's not that. My point is that there are different forms of abstraction, that there are different traditions and methods that are rigorous of abstract thinking that are not necessarily mathematical. They may operate with mathematics as well to improve, you know, data or reliability or whatever, but the essence is not mathematics. Biology, experimentation in psychology, cognitive sciences, etc. Everything that has to do with empirical science, that is also rationalism, but it is not necessarily, and it's not a priori mathematical. My point is, so my question is, or my suggestion is that perhaps the more generic term is formalism, the ability to think formally as per formal procedures, rather than, you know, just mathematically. My point is that scientific formal thought is not the same as mathematical thinking. I am not trying to humanize it, to make it more, you know, relatable emotionally or whatever. I am just saying that there are different forms of scientific rational thinking. To me, Saussurian linguistics is one of the most precise forms of scientific thinking, and it does not operate with any form of mathematics whatsoever.
Yeah, okay, well, I think we can draw a distinction then. I do think that I would say that, like in the Gödel example, and Darwin, to use that as an example, or in the case of structuralism, I think you can formalize them. Always, yeah. Like I think you always could come up with different symbol systems and formalize them. In Darwin's case, for instance, he didn't, but lots of people have. The 20th century is full of different formalizations of you know, his work, and a lot of them I'm working with now. Right, they've turned his work and selection models and so on, evolutionary models, into math, you know, into equations. And the examples I was giving before, yeah, we're all examples where we're crossing over, we're crossing back and we're crossing over. So I think I would say that, yeah, I think like if that's really the fundament of the question, I don't think it's always useful or the best choice to do, you know. And yeah, I didn't mean to say that I thought that you were, you know, that there was a kind of soft hard kind of dichotomy going on or anything like that. I didn't think that, but I was more trying to say that, yeah, I guess I do think that you can always take words and then invent a calculus. You know, you can always take words and then kind of atomize them. And this is sort of the formal language, you know, kind of gambit that, okay, people can say things, they can say them rhetorically. And if there's a rational component, if there's an argumentative component, then yeah, I mean, if there's a poetic component, if there's any component, you know, I think that you can sort of take that. And to me, what math offers is this just incredibly deep kind of language, you know, that then when you recompare it with that, just gives you a huge map of what's going on. And I think you could go to each of these examples and create mathematical equivalence, you know. In a lot of cases, I don't think it would be necessarily, you know, helpful. But, you know, I guess at the bottom of your question is, well, what's the essence of rationalism or the ratio, or, you know, this sort of, you know, we have this much of this much of that, or we have, you know, a sort of rational argument from getting from A to B to C. And yeah, I mean, I think that this is that you can just find different ways of doing that. Now, when I get into all the geometries and so on, this is definitely, it's getting into a different space, right? It's getting into a different space that, again, I think would be in a lot of ways less effective, you know, to do that. And when you have a rhetorical argument, like, do you visualize it? Like, will it be helpful to do that? Absolutely, I concede that it's not talking about the totality. It's not talking about the most effective different versions of it. But yeah, for better, for worse. I mean, another way to think about it is that what language is doing is working in this sort of arithmetical, algebraic kind of space. We can condense it into that. And what geometry is doing is this sort of parallel space that's sort of going from the pictograph or the letter, and it's abstracting in different ways there, right? Which you could go to visual.
Absolutely. I mean, I agree. We're both aware, I'm assuming, that what we know as artificial languages now, what we know program languages, I'm sorry, or artificial even, so the opposite to natural languages, relies on Saussurian knowledge, you know, Syrian science of language about natural languages, in fact. So that is the foundation. From that point on, there is further and further linguistic formalization branching out. You still have, like, for example, Chomsky's early works. That's not mathematics, but it's still a high level of further formalization of Saussurian grammar, right? So going into the direction of what he used to call universal grammar, right? Yeah, right. I think so. But that's still not, you know, mathematics. Then mathematics comes in. So it's not a case against mathematics. I'm just trying to suggest that maybe what is rationalism, or what is a scientific procedure of thought, of execution of proof, for example, or examination of a matter, that is maybe something wider as a category, and then mathematics, and maybe it should be called formal thought or something like that, you know, to be more. So that category would include mathematics. It's not excluding it. It just allows for other forms of formal thinking.
Yeah,
Algorithmic
well,
thinking in a way, you know,
sorry?
these are procedures of thought. I mean, I've studied linguistics, you know, so serial proper linguistic, comparative linguistics, you know, it's a rather, I don't know exact thing, but it's still not mathematics, you know.
Yeah, well, I mean, you know, one thing I'm thinking about is, I don't know. I think that like there is, I think it could be. I mean, that's the short version. Like, I think you could formalize, like I think computer sciences have formalized a lot of Chomsky's grammatical ideas. I think it's, you know, again, we've got this cultural kind of thing going on where you could with Saussure, but there's you know, there's this Anglophone world and there's a sort of what's science and so on. And I don't disagree at all that there's all kinds of formal characteristics. And I think you could put it into, you know, into a formal thing that you could potentially call mathematics. I mean, you know, are the diagrammatic things that Peirce doing, are they mathematics or not? Well, you know, I mean, I think that I definitely don't disagree that, like, I don't think that mathematical rationalism encompasses rationalism. And I do concede that, you know, you're probably right that there's different ways to specify. If I'm going to go deep on math and math toolkits, and I'm really looking at what I have seen within these papers, because really my thing is just these open science workshops, and I'm thinking about, well, how can I now go from the things of the lab, which I've been doing for like a decade, and now I'm looking at the things of the publication, and I'm looking at all these publications, and I'm trying to find a common language for all these things that are going on. And what I've presented is my kind of, okay, well, then once we've seen that whole system, how can we start learning it and building up a toolbox so that when you go to those papers, you can make sense of what's being done. And so this is sort of this kind of drive of creating a toolkit and creating alternative toolkits for doing that. And that would absolutely include things that don't necessarily get into geometries and so on. But within science, I mean, I just, like, I've been in all these different science labs and all these different contexts, and there's such a graph fetish, you know. It's like within, I don't think it's necessary at all, right? But there's definitely this thing where that geometrical reasoning, because one distinction I was thinking is that I think that these more the human side of sciences, or these sciences of sociology and linguistics and so on, they tend to be better formalized within an algebraic arithmetic context, where all the logical examples that you're bringing up, I think, can work between a more symbolic character system that you don't have to call mathematics, but that you can formalize that way. Whereas geometric ones tend to be the natural sciences, this sort of earth and sky thing, right? And if you're working in those sciences, then yeah, I think it's sort of like, well, why would I do all these graphs, right? Why would I do all these geometries when, you know, I can describe everything I want to say in a very, very rigorous formal way, with language or with some basic notations, or, you know, what have you. And yet, if you go into a psychological science journal, social science journal, again, all kinds of conventions there, all kinds of what, you know, this Anglophone kind of cultural NATO bubble is doing and how that's disseminating. There are graphs all throughout. And I'm like, okay, well, I want to deconstruct and reconstruct that language. Your point is at the core of it. Well, you don't need to, and there's no reason why we have to have these at all, right? Or anything that necessarily gets to anything that we're defining as mathematics. Absolutely. But given what these new science writers are writing, given what's in the journals and the techniques that they're using, my only point is that there's a lot of it present, you know, and this framework that I cause is a way to get there. Is it the best to posit in relation to rationalism in general? Yeah, absolutely. Your point is taken, right? That you know, doubtfully, and then also using another language might shift that, right? In a way, sort of to take that word is I don't know, provoking mainstream. You know, it's sort of taking what is the accepted and sort of just inserting it in there and seeing, you know, well, here's some things, and then let's insert into the scientific method kind of debate and use that as the framework for what we're talking about, as a way to say, okay, you're claiming the science name, and then you're using all these graphs. Well, what is that language? What's going on? You know, you won't write an anthropological paper. And this is, again, within the science identifying side, right? Not to say that there's all kinds of anthropology, or, you know, that isn't also using rational methods and so on, which, again, this is your point, is just a point taken. But they won't use that science label, you know. And and they'll be anti it and so on, and that'll be bad and lead to bad consequences and so on. But if they take that label, suddenly there is very consistently, and I mean, I see this as two authority bias kind of qualities, that within the more humanities identifying, you have more of a citational bias, and within these science identifying, you have more of a structural machinic kind of bias. You know, you have the apparatus and the person, you know. So a figure like Darwin becomes more and more entrenched within that. So yeah, it's a kind of skeptical, critical, creative approach in relation to those branches that very consistently have these things that, for me, yeah, it's best framed within mathematics. But the critique that you have is it's not essential to it that I use that, and that, you know, that sort of that focus on aspects of rationalism. I mean, certainly, yeah. I mean, there's all kinds of use within, say, I don't know, Hegel's use of rationalism or something, where there's not enough formalization for me that I find useful to get to this dissection and recreation, you know, of how the science paper is constructed. You know, how do you display results in a science paper? What's going on there? What's really the scientific method there? Well, it really is a mathematical commitment or bias or sort of game that's always being played. That's definitely not the depths of rationalism, but is a type of rationalism that, or a type of formalism or mathematicism that's consistently used, and so on.
Okay, thanks.
Was there a second question?
No. I mean, that could be, but
there could be, but yeah.
My dog is barking, and I have to take him out. So I'll have to stop.
All right. So thank you for the brilliant talk. It was a pleasure to have you. Oh, there's another question.
Let's do it. We're here.
Okay, wonderful. At the end of this interesting topic, what do you think is the role of rationalism in the modern scientific fields? For example, especially in the physics in quantum theory, where the quantum mechanics is mostly mathematical, and if you see it from a rational point of view, the theory is completely counterintuitive, and it goes against our experiences from our world.
Yeah, that's an awesome question. Sorry, my Cyrillic is very bad. I want to be able to use your name. I don't know if you can write it in Roman, but anyway. But thank you for your question.
My name is Dimitar. You can call me Dim for short.
Dimitar. Okay, Dimitar. Awesome. Yeah, great question. I think this really gets to the core of, well, I mean, this is honestly, this is Katerina's point, right? Like, she kind of made this, and, you know, we're getting back to this, like, on the one hand, we have scientific method, right? And its claims. And then you've got, well, okay, let's deconstruct the kind of empirical, what I call this empirical provincialism, and let's look at the versions, the rationally oriented versions that actually took up what was going on. So they took up Newton much more than they took up Bacon. They take up Popper much more than they take up Mill. And then we have all this work that has led to things like quantum, right? We have this sort of progression of mathematical commitment. There's this great, I just read a great Einstein book where there's this point where, you know, he's got these intuitions, and then eventually he just had to give up and follow the math, they say, you know, because he just, like, it just didn't work anymore. And this is kind of latter career, post general relativity, and so on. So then it's like, well, this is kind of Katerina's point, and this is the point, the point of distinction that I think I can I can better articulate now as what are the rational approaches in orientation to scientific method that were taken up versus what rationalism is, right? What can a rational approach do? Scientific method is definitely in the former category, right? I think Katerina is right at the center of identifying this rift, and your question is as well, right? So is it following rationality, as you're skeptical of, and as you should be, because in so many ways it's not, right? Is it following, however, this tradition that has come out of the self-identifying science version? Let's go back to the root of that science, that people who come to identify with science are part of, there is this kind of utilitarian undercurrent or this careerist kind of element that leads to the coining away from natural philosophy with a broader rationalism to something that is more utility oriented. One of the great physicists working, there's a number of people working in, say, loop quantum gravity that have some great critiques, not just of, you get from quantum, you get to string theory, you get to all the different fold theories, and we're quantizing gravity, and they're following the same trajectory. They're all part of the same conversation you're talking about, Hossenfelder calls this lost in math, and other people are looking at how they're building these colliders, and they're doing all these things that in no identifiable way has rational components that we can work with, but they're following the machines, they're following the math, and I mean, the implicit point is that, well, you're not rational, right? You're following math to numerology, you're following math to something that's not. How do you frame that argument? How do you get into all the diagrams that are being used and this tradition of science identifying components of rationalism and then bring in the full gamut of different rational elements, which is really what this toolbox is about. While going from those received ideas and diagrams, what is the fetish? How do we strip it away? And how do we get to a more grounded argument? And then bringing about, how do you formalize that critique? How would you write a paper that critiques these mathematical formalizations from a rational perspective? That to me would be an awesome paper, right? But how would you do that in a way that they would listen to it? Well, you'd have to use a lot of their language. You'd have to dissect a lot of their formalisms, right? You have to get under the skin of what's sort of going on, right? Because what's the broad sweep of what defenses and attacks might be is that, well, look, this is what these experiments have led to, this is what these equations have led to, and I think you just need to learn more math or something, right? Like this would be sort of a defense, right? And then you would say, well, I have. You'd have to say this, right? This would have to be, and then you'd say, well, this is what's being talked about, but this is where, you start to identify fissures, and this is where these physicists are interesting, because they say, well, we're doing this kind of casuist path, this Kuhnian janitorial kind of model, if we're just doing these experiments without having a good hypothetical framework, right? Hossenfelder is critiquing, for instance, the Hadron Collider stuff. We keep doing these experiments, we keep splitting particles, we build out the standard model, but we've never gone back to address some fundamental questions, that of unification, say, and of dealing with the equations we have via Einstein or via different unificationists. So that's one way in which physicists are sort of taking a tack that's related to what you're bringing up, and then they mount a critique. That's to say that there's all kinds of ways I think you can make that sort of critique. There is a rationalism there for sure, but it is just the rationalism that I think Katerina was taking issue with. It's a rationalism built within the self-identifying community that has these paradigmatic limits, that doesn't see outside its own cultural biases, and is committed to what we can do and what's sort of producible and what equations can we build on and what's the community we've come into, They're critiquing all the American-centric element, for instance, of the quantum aspect, when they sort of rejected Einstein in this post-war period, and you've got Feynman and the rest, and they're sort of building up from this, and they're leaving the fundamental equations because this is philosophy. This isn't science, right? Well, you've also left a lot of rationalism behind, right? You've also left a lot of your potential toolkit, So yeah, it's a bit of both. There's definitely a logic. The more you get into it, the more you make sense of that logic, as much as, it's what the hell is going on. I use an example, for instance, of when you have the double slit experiment, you can think of statistical height measurement. You don't know any one thing, but you know a general trend, right? And we tend to have mystifying ways of explaining it, which is a science communication issue. There is definitely a logic within what's going on, but it definitely has these limits. It has these limits that you brought up, that Katerina did, and that are again this rationalism in relation to the scientific method versus what rationalism is. and yeah, and that would be, let me just say that if, you know, for something to pursue or for something to go with, that, you know, when I'm teaching and talking about this, I would love that kind of a trajectory to sort of to explore.
Thank you for your answer. It is an interesting remark that you mentioned Einstein, because for most of his life he was against the quantum theory. He did not support it, and he argued with some of the founders of the quantum theory. But when the empirical evidence started to pile up in support of it, he had to grudgingly accept it.
And not only that, but he started it, you know, like the photoelectric effect. He won the Nobel Prize for the work in the photoelectric effect, and special relativity is deeply tied to, you know, what was making these steps towards, I mean, quantizing is the photoelectric effect, is that the photon particle-like can hit out an electron, you know, and you look at a Feynman diagram and it's, you've got, you know, this is what's sort of going on. So he kind of started this, you know, but as you're rightly saying, he was like, you know, he was like, whoa, you know, like I'm not into this. But yeah, there was, I mean, it was the same with relativity. People did the expansion, for instance. He was like, no, I'm not into that, right? But then he's like, okay, like he kind of jumps on board, you know. Well, I mean, and that I think is a partial answer to your question, and also a way in for you, that if you want a critical tack on that, you can look at how these elements of rationality and whatever thought evolve in relation to what the math is producing and what the experiments are producing, you know, because like whatever that issue is, so you take X quantum theorist that is saying things that for you just are whatever, right? And you say, okay, science communication got that wrong, but this is actually in their theory. And when we look at their theory, you can see that it's because they came out of this context of following these equations and following these sort of experiments, right? And in Einstein's case, you can see how, yeah, okay, he bought into that, but Einstein would be a great figure to look at because you know that he's still got some reservations about X and Y, right? The EPR paradox is all about this, you know? So he would still have this sort of, okay, I concede X and Y, but Z, you know, thinking rationally, do, you know, like this is what the expanded toolbox is, that, you know, we've got other ways. Here's critique A, here's critique B, you know. And I mean, I think we just had a demonstration of that, because to me, it's like, okay, well, here's what is rationalism, and yeah.
All right.
Sorry, yeah, so I think we just had a demonstration of that. Just a moment, Isidore.
All right, so thank you for the brilliant.
We've got lag. Yeah, okay, I'll just add it. So I think that yeah, the back and forth we had right before you and I, Demeter, is just this, that, well, look, here's rational possibility, and here is how it's taken up within the quantum community or within certain linguistic communities. Well, look here, let me reason, let me take you to these foundational moments, right? Using different rational systems from other times, from different spaces, you know, whether mathematized or not. And that way you can sort of, you can start to, you know, sort of take it apart. Key to that quantum community, and I guess my contingent kind of focus is about this, that key to that quantum community is learning enough of their language, you know, that your critiques coming from different directions, you know, will gain airtime, you know, actually enters in the conversation, can be in their fora, in their conference, in their journal, this kind of a thing, which for me is in a way reducing a lot of what you can do, because you're going to those communities and you're, in a sense, buying into the thing you want to critique more than you might, and maybe changing your mind, maybe not, maybe reinforcing, disagreeing even more. But in order to make that point, you're sort of, you know, specializing that focus in order to then be able to make that more general point. But yeah, awesome question and provocations. Thank you.
We're a bit over time. So I want to thank you for the brilliant lecture. We were very excited to have you. It was brilliant. We hope to have you again and to see you in the near future. And thank all of you for the brilliant discussion. Our next open seminar is from Tarvu Varis and Samantha Bankston, and it's on the 24th of August. It's on fragile metaphysics, so you can register there through our site for that one.
Thanks
so everybody.